Okay, I think it's a bit past 1, so we'll start now. So hopefully they can hear us on Zoom. It looks like the microphone's working. Yeah, so today we have Shirley Lee. She's about to be faculty at UC Irvine. She obtained her PhD from Ohio State University with John Beacon before moving to the SLAC particle theory group for the first postdoc. She's currently finishing her second postdoc at Fermilab before she moves on to her tenure track position at UC Irvine. So today she's going to talk to us about neutrino-nucleus scattering in neutrino oscillation experiments. So go ahead.
Thank you, Tom. Although I have to point out that you made a great advance to calling my PhD university Ohio State University.
Okay. Oh
it is the Ohio State University.
Trademark.
Yep. But yes, otherwise, thank you very much for the introduction. And today I'll talk about neutrino-nucleus scattering of neutrino oscillation experiments. So specifically, I want to discuss couple points. First is how well can we theoretically compute neutrino-nucleus scattering cross sections right now, and also how does this mismodeling or theoretical uncertainties impact experimental searches. So I just a couple of points to explain this. So first, none of the work is discussed is my as any of official collaboration members. So this line of work basically just as curious theorists. I want to understand a couple points. So first, our current neutrino oscillation experiments have fully included the theoretical uncertainties relevant to scattering cross-section. And also, experiments have to deal with this uncertainty somehow, and whether there's any theoretical guidance we can provide for experiments to better account for these uncertainties in this modeling. And lastly, if current theoretical calculations are not accurate enough, for instance, for next generation neutrino experiments, then what are the precisions that we want to aim so that they can achieve their design goal? Okay, so that's the setup for my talk. Please interrupt me with questions at any time. Okay, so just to make sure that everyone's on the same page. So this is the standard neutrino oscillation paradigm was established experimentally over the last 20 years. So hopefully you are familiar with the quantities on this figure on this slide. So basically what discovered is that there's 3 neutrino flavor eigenstates, mu, mu, tau, and there's 3 mass eigenstates, mu1, mu2, mu3, and these 2 bases are not aligned. And then they're connected by rotation matrix that's parameterized with mixing angles and delta CP base. In addition, when we want to compute neutrino oscillation behavior, we also need to know the mass square splitting differences and additional parameters in the standard oscillation framework. And right now, between the left and right configuration, we don't know which one's correct, and that's the so-called mass hierarchy parameter. So hopefully that's all standard and you've seen. And I just want to say that for these 5 parameters, I think it's fair to say we've entered the precision era. Well, right now we're measuring these parameters at a few percent level. And the last 2, what can be called unknowns, and delta CP and mass hierarchy. And these 2 parameters are the bread butter measurements for next generation neutrino oscillation experiments across the globe. And just to see the progress more intuitively, here I plot the 1 sigma error of the mixing parameters and their evolution as a function here, just for fun. So one thing I actually find kind of interesting is that by 2040, which is after the nominal exposure for next generation experiments, we are able to measure neutrino sector comparably to the precision of how well we're measuring the quark sector oscillation right now. So the last column of black points that shows the current accuracy of the CPM corresponding parameters that we currently have. So I don't know how you feel about that. I actually thought that was hugely impressive, so I was very happy about that. But we won't get there till 2040. Okay, and I think this is perhaps what most people think about when we think about the experimental neutrino, program in terms of measuring standard oscillations. But this only shows, let's say, half of the picture. What's perhaps even more interesting is the surprises that we see along the way. And there's a bunch in the data over the past 20 years. Probably the most famous 2, I would say, are the short baseline anomaly that's on the left and the reaction neutrino anomaly on the right. So roughly short baseline anomaly is probably best illustrated by this mini boon example where they measure electron neutrino. That's the x-axis neutrino energy. And you see that especially towards the lower energy, the data points are overshooting over the theory prediction. So they see a excess of E-like events. So if these are actually electron neutrino events, then the current framework cannot explain where they come from. But of course, they could actually be not due to neutrinos if there's mismodeling of detector background, etc. And the right, it shows the reactive neutrino anomaly. Basically, look at the average of the blue line. That's the average reactor neutrino flux detected from a bunch of experiments. And you just see that it plateaus to something like 0.94. And that's the average neutrino flux compared to theory prediction. So basically, we're roughly missing 6% of the neutrino flux coming from reactors from a bunch of experiments at different distances. And intriguingly, both anomalies could possibly be explained by the existence of a 1 eV stereo neutrino. However, there's a huge caveat to that. Right now, if we add 1 eV stereo neutrino to all the global data, that does not provide a good fit. So because when we say 1 EV, that's a rough number, but it will specifically, if we are trying to pinpoint the parameter space, there is some tension between various data sets. So the status of this is not clear, but there have been very active activities going on till now trying to understand these. So for instance, on the left, as hopefully people here know, recently, as of last year, Microboom finally put out their analysis assessing what's happening with the mini boon access. And basically, they put out the first analysis. It's not conclusive. So right now, there's huge debate in the literature in terms of people trying to understand how the microboon data sets add to the global picture. And similarly, on the right, there has been continuous effort trying to understand reactor flux, whether the problem exists actually in the possibility of a stereo neutrino, or it's just with this model reactor neutrino flux because it is very difficult. So both are very active right now, and the jury is out. You just have to stay tuned. Okay, so that concludes my introduction of physics motivation. So at this point, I'm just going to assume that everyone in the audience is really, really excited about neutrino physics and about all the possible physics, plus what use cases that these experiments can deliver. No, so our goal is that given that we want to know the results of this analysis, then we want to know that the results we get from experiments are correct, then all the error bars are correct. And one of the leading theoretical uncertainties contributing to the uncertainties of experiments is so-called neutrino-nucleus scattering cross-section problem. So that's the focus of my talk. So to better understand this problem, especially the status of the problem, we should go back to the beginning. So I would say experimentally, this problem was identified quite early on by mini boon. So earlier I showed the mini boon is one of the experiments that see the axis of the electron event, which is very important. But almost equally importantly, they discovered an important problem. So this was back in 2007. And basically, they measured the following quantity, and it's called axial mass. So if we try to compute how a single nucleon interacting with a weak current, we can write down the matrix elements. Then based on basic physics arguments, we can write down the form of the terms. And one of them is called axial form factor. Essentially, it's one term of the cross-section and the normal way to parameterize it is dipole form. And again, it's something simple that fits it pretty well, so that's very commonly used. But the value of MA roughly just grows with cross-section. So larger MA, larger cross-section. And mini boon try to measure this quantity, and that's shown in this figure, cross-section as a function of neutrino energy. So what you see is that without the mini boon data set, so without looking at the red data points, all the previous theory and measurements sort of agree. So here I'm talking about these types of data measurements with all the dashed lines and dotted lines, and you see everything sort of agree with each other. And numerically, that roughly corresponds to the value of MA about 1.0. It has error bars, but roughly here's what we're talking about. And mini boon came online, decided to measure this, And these red points are what you see. You can just see by eye, though you shouldn't, but you can just see by eye that clearly mini-boom data is inconsistent with the nomad data. It's clearly much higher. And then if you were trying to fit this, what roughly came out is that the mini-boom measurements of cross-section corresponds to MA of 1.3, where earlier everything agreed with 1.0. So this was really unexpected. People didn't really think this was going to be a problem. But then suddenly this thing disagreed, and then there's huge effort trying to went in to understand what caused this, and basically opened up. And the more people look at this, the more people realize that, oh, this is worse than we thought. And I would say right now we're sort of still in that stage, basically trying to identify all the possible problems. And hopefully that we are almost identify all the problems and can start to address them as a field overall. Okay. So that brings me to the outline for talk. So first, I will just discuss the basic experimental setup, and at a very, very base conceptual level, discuss how the cross-section calculations actually enter experimental analysis. And then next, I'll basically describe conceptually how the cross-section calculations are done and why they're so difficult, and roughly what are the size of uncertainties. And last, I will discuss how the cross-section uncertainties actually impact new basic searches. Okay, so let's look at the first point. So for the rest of the talk, I will follow, it basically applies to the so-called long baseline oscillation experiments. These are accelerator-based experiments that's sort of taking the center stage for oscillation experiments in the US. And you might have heard of T2K and NOVA, that's current generation, and next generation that applies to DUNE and Hyperk. And they all follow a similar setup, at least for the purpose of this talk. So we have an accelerator beam that makes GeV neutrinos. And then what we want to measure, and the flavor is governed by mu. What we want to measure is how these GeV mu have oscillated over 1,000 kilometers, and how much of that have turned into mu-e. And then we want to basically measure this neutrino mode, mu to mu-e, and anti-neutrino mode, mu bar to mu-e bar. And these combined can give us delta CP, mass hierarchy, and essentially all the other oscillation parameters precisely. And right, and but because we know that the accelerated neutrino flux have pretty large uncertainty, and there's also large uncertainties in cross section. So we put a near detector right next to the beam. So the idea is that because it's so close to the beam, there's no neutrino oscillation happened yet, so it sort of measures the control sample. Okay, so this setup is what you should keep in mind to understand the component. Okay, and first, let's just to see conceptually how would you measure neutrino oscillation probability. Very, very simple. So let's say what we want to measure is oscillation probability, mu to mu-e, as a function of neutrino energy. Something like this. And now let's see what would you actually measure in these detectors. So the oscillation probability is just the flux at the far detector after oscillation divided by the flux at the near detector before oscillation as a function of neutrino energy. Now, very naively, conceptually, the flux is what you measure in terms of event rates, but divided by total cross section. Hopefully, this is straightforward. Okay, and similar thing in both far detector and near detector. Okay, so if you look at this, you realize that because we measure the event rate directly, it's just neutrino event as neutrino and event rate as a function of energy. And this cross-section calculation that enters is this total cross-section. And when the flavor is different, these cross-sections are a little bit different, but that's a stability effect. And there's plenty of awareness that, there could be differences and there are people calculating them. So let's say to first order, these two cross-sections are the same. Then that just drops out. So then to first order, it seems like the only thing you need to do is measure event rate in near far detector, take a division, and we don't need theorists. Which depends on how you feel about it, may be a really good place to be. And I think in the neutrino community, sometimes people call this near far cancellation, and I think conceptually that's what it implies. So however, obviously it doesn't work. And why? Because when I write down this equation, notice that I have neutrino energy everywhere. And when I write it down, if I want to directly relate to oscillation parameter, that always means true neutrino energy. But the problem is neutrino is not a charged particle, means we never directly observe neutrino in detectors. So there's no way to measure their energy directly. So what we have to do is measure all the charged particles they produce and reconstruct neutrino energy, where all the systematics come in. Okay, so just to look at this a little more detail. So how does cross-section calculation actually impact energy reconstruction, which is really the key? Okay, so we have to talk about detector technology a little bit, and I will use DUNE as a concrete example, but it really doesn't matter. Conceptually, it's the same idea applies to all kinds of neutrino detector technologies for long baseline experiments. So imagine DUNE is a large box of solid uniform box of liquid argon, and it sees all charged particles above some thresholds. So a neutrino comes in, you don't see that, it's hitting argon 40. And because this is an oscillation experiment, we want to look for charge current interaction. So it gives you an outgoing lepton neon. And then because there's a few GeV of energy, you would additionally knock out some protons, pions, and neutrons, etc. And they tend to have energies of a couple hundred MeV or so, let's say. And all the charged particles would leave tracks in liquid argon detector. And you don't see neutral particles. In this case, the system just has neutrons. That's neutral. So I realized that I did not get rid of this. Let's try to forget about that. And if this were the case, then how would you reconstruct neutrino energy? Pretty straightforward, because you can measure the energy of all outgoing particles. So you would add them up, and that should equal to the energy of the neutrino, just based on energy conservation. So if this were the case, what you would conclude from the formula is that, okay, I can recover everything in my detector. The only thing I'm missing is the energy of the neutrons, because I don't see that. Which means the only prediction I need from theorists is how neutrinos are producing neutrons, what's their energy fraction, etc. Because that I don't see. For anything I do see, pions, protons, muons, especially for liquid argon detector, you can see them so well. Even if the theorists predicted wrong, it's fine, I can correct it in data. So this seems to indicate that the only part of the cross-section I care about is neutron fraction. And unfortunately, that turned out to be not the case. So here, this figure shows a simulated neutrino interaction in liquid argon. And just like the previous conceptual illustration, all the charged particle depositions and tracks are illustrated with colored points. So what you see is neutrino interaction happens at 0, 0. And indeed, the muon leaves you a pretty clean track. And so that's very easy to measure. And then protons and pions also gave you nice tracks, which is good. But the problem is, you are sitting inside the interaction point and filled with liquid argon. They will reinteract. So then for this particular case, proton and pion further reinteract, split into multiple things. Meaning that during this process, there are certain energy losses. And then you might also see this purple cloud. And so it turned out that those are from neutrons propagating in argon, leaving energy deposition. So it turns out that protons and pions are not 100% visible because of this reinteraction. Neutrons are not 100% invisible, again, because of reinteraction. So, and at least I think for the neutron case, it's easy to imagine that it's very hard to calibrate it, meaning that when you scoop up all the charges from this region, you will collect some fraction of neutron energy. But it's very difficult to know what's the efficiency of the neutrons you actually collected. Essentially, similar ideas applies for protons and pions. So when it turns out that these hadronic reinteractions are actually crucial in argon, and which means translate to cross-section calculation, meaning that we actually need to know, for instance, what's the energy goes to proton versus pion, because that affects how much energy is lost to detector quenching. We also need to actually know the energy spectrum of these particles, because even though the thresholds seem very low for the primary particle, keep things re-interacting and particle spectrum keep getting softer. So way more energy actually get lost below thresholds, as you would naively guess. And even how many number of particles produced actually matters, because it affects how much energy gets into nuclear breakup energy. So the unfortunate case is that we need to understand all the exclusive aspects of the cross-section prediction. And they would play a role in energy reconstruction. So just to be very clear, what we need is the fully differential cross-section from theory prediction, not the total inclusive cross-section that we would naively think is near to far cancellation. Okay, so that's concludes the part of roughly why we need cross-section calculations. Are there any questions at this point?
On slide 14, was that this is the simulation,
This is a simulation,
and this is simulation for one neon mu.
correct, for 1 4 GeV mu
So you-
example.
Is that many neutrons or that many depositions from this?
It's one neutron that's deposited in this blob, whole blob.
Is it really?
This one, I think there's 2 primary neutrons. But this is very typical of a neutron. It just, that's
Yeah, it's
sort of like
bouncing back. and
the
forth.
unfortunate case of argon, because it does not stop neutron, unlike any other neutrino detectors. It just keeps bouncing around.
I see.
Yes.
And do you know roughly what is the energy? deposit
Yes,
single
For this
interaction?
example,
Per single point, I guess.
so because this is a 4 GeV event, I think 1 neutron is something like 300 MeV, 1 neutron is 500 MeV or something like that, like a 200 MeV neutrons at the primary vertex. Right, another point that adds on to, okay, and sort of adds on to it is there's further neutrons produced from proton pi interaction that adds to the blob. But so you see
I see.
some orange points and green points, which might be a little harder to see, but
I see.
like yeah,
Okay.
they just don't stop in argon, which is kind of unfortunate.
I did not appreciate how many interactions there are. Thank you.
Any other questions? Okay. So next I will discuss just briefly conceptually how we actually compute these cross sections and what would the current theoretical uncertainty be. Okay, since we're going to be talking about numbers, I want to just set the scale of the problem. So let's say if we can quote one number in terms of how precise the experiments are operating at. This is example. So again, I'm using DUNE as a concrete example. Here again, the usual oscillation probability as a function of neutrino energy. So here I chose 3 delta CP values to illustrate this probability. So 0 and plus minus 10 degrees. So 10 degrees is the nominal 1 sigma accuracy that DUNE aims to get after their nominal 7-year exposure. So roughly speaking, the experiments want to tell apart the 3 curves. And neutrino flux peaks at 2 to 3 GeV. So most events would come from the largest one. So you see that the curve, differ by, I don't know, 5% or so at the peak. So that sets a scale that this is roughly, a few percent precision experiment. Okay, so now let's see how well we're doing on the cross-section side. So let's say the goal is to compute a neutrino interacting with some nuclei. And the key is neutrino beam energy is between 0.5 GeV to 5 G. And first, this calculation can be divided to 2 parts. We just start with computing a single neutrino interacting with a single nucleon, a free proton or neutron at rest. And sometimes this is called the primary vertex in this field. And the second part is to essentially modify the cross-section vertex and taking into account the fact that this happens inside a nuclear environment. So for instance, this proton and neutron is not free at rest, but rather they're moving with Fermi momentum and bound in the nucleus. Okay, and I think looking at the second part, maybe it's a little easier to appreciate that this is difficult because the second part essentially is the nuclear structure problem. You want to solve how protons and neutrons are doing inside argon nucleus, which is, nucleon number 40, so it's fairly big. But what they will sometimes underappreciate is that even the first interaction is still difficult. And Why is that? Okay, so even though the beam energy only spans about 5 GeV, this actually spans both perturbative and non-perturbative QCD. So at the highest energy range, let's say 5 GeV or so, we are sort of in a deep inelastic scattering regime where we have the nice spectralization and we know how to compute things, and the hadronics degree of freedom, of course. But if we go lower to energy, let's say a couple GeV, then we start to see variable resonances showing up in the final state. So for instance, the probably most famous one is excited state of proton, which is delta. These variable states would then further decay, give you a nucleon and a meson, like a pion. And once we go to the lowest energy, say 1 GeV, the hadronics degree of freedom are just nucleons. So the neutrino is basically swapping protons and neutrons. So in this energy range, basically the hadronics degree of freedom go from quarks, partons, variant resonances to nucleons. So there's simply just no control expansion that can cover the whole phase space. Again, because we're talking about energy range of, basically 1 GeV. Meaning that there's really no control theory calculation we have. Also, equally importantly, this means that the theory calculations do not give you meaningful error bars, which is of course very important for experimental analysis. Okay, so if we want to assess theory uncertainty, then what options do we have? Well, compared to data. So luckily, in the past few years, there's a lot of great neutrino scattering data coming out of this generation experiments. And here I show 4 examples. You don't need to look at the 4 plots. Just look at the first one as an example, where this is some measured of neutrino event rates in NOVA. So the data points is the black points with very small error bars. The theory you should compare to is the top of the blue. So you can see that especially at around 0.1 GeV also, there's a huge discrepancy between data and theory. And we can look at all of them in detail. Basically, the story is consistent. That even though the neutrino data is still kind of coarse, right? We're talking about, reasonably large error bars of the data. But even at this level, there's already no current combinations of theory with varying parameters that can reproduce all neutrino data set. Thirdly, indicating very large mismodeling and uncertainty of theory calculations. Okay, any questions at this point? No? Okay. So, but this data is not very helpful in terms of diagnosing the problem. So this shows discrepancy, but which region of discrepancy and how can we improve it? Okay, and it turns out that there's another data set that's hugely helpful for this, and that's electron scattering data. So just to be clear, there's a lot of data where you have a monoenergetic electron beam hitting either a proton or a nuclear target. And then you put your detector at some fixed scattering angle, measure the energy of the outgoing electron. So basically recording double differential inclusive cross-section. And just to be very clear, this cross-section, of course, is dominated by photon exchange process. So you might look at that thinking, well, this is, has nothing to do with neutrino interaction. Why is this data set helpful? Well, even though the electron part and the exchange boson is different, the difficult part of the modeling actually has very large overlap with neutrino interaction. Because keep in mind, the difficulty is not how to compute the lepton vertex. We know how to do that very well. The difficulty is how to model the hadronic side of a nuclear response. So basically, the modeling is actually the same. So for instance, if we try to write down the elastic scattering, this is how we will write down. We can write down the matrix elements of the interaction, and the difference is the current squeezed in the middle. But the point is, if we know our theory framework, meaning that we know we can express the matrix elements in the following form, if that's legit, that should be correct for both cases. And then the thing that you need to compute or you need to measure are these form factors. And in electron scattering, because it's a vector card, it just has essentially basically half of the form factors. So if from electron scattering, we can pinpoint the theory and we can measure half of the form factors, we basically solve more than half of the problem. And additionally, there's nuclear effects modifying the cross-section. That's obviously the same for both electron and neutrino scattering. So there's many of the theory modeling pieces that are shared between these two cases. Okay, so this should help inform us how neutrino event generators are doing. And this shows one example where the electron scattering data is 2.4 GeV electron proton at a scattering angle of 20 degrees. And this data is measured at JLab, and it's the same in both left and right panels. So overlaid that, I also show the theory calculations for the exact same process, electron scattering. So it's really apples to apples comparison, and reviews how generators are doing. So in the left figure, it's the generator called Genie. It's probably the most popular used event generator by experiments. And the Genie calculation is the solid purple line. And you can see that it disagrees with data by quite a bit. And the right shows a different event generator people, where the total is the green line, and you can see it doing much better. But that's not very helpful aside from just getting one number. I would say the left maybe has a mismodeling of, I don't know, 50% or 80%, and the right is at about 20%. But we want to understand what went wrong in these calculations. And here electron data are specifically helpful. So for one, we can see these sharp peaks. So that's clearly resonance production in this region. And where both, I would say both generators do reasonably okay at about maybe 20% uncertainty. But the problem with with Genie is that it has a very high DIS component that makes the total cross section go above. And seeing this, you might be surprised because normally we would associate DIS with something well established. They should have smaller uncertainty, and generators should agree on what DIS is very well. But here actually we see the opposite, that DIS has very large uncertainty. And the reason is these are labeled as DIS computed following DIS formula, but this is not a region of phase space where we expect factorization to work. DIS should apply to Q-square of in the limit of infinity. But here, these events have Q-square of about 1 GeV, very far from infinity. But the issue is there's no well-established alternative theory that we can compute this region with, which has very large uncertainty. So, and this is a fairly recent study that people are trying to quantify this region. This is what I meant by, we identify this problem, understand there's a problem back in 2007. Back then, people identified problem in a different region. And still recently, we're trying to understand of all for the entire phase space, which region we understand at what level, because the theory modeling going into different regions are very, very different physics. Okay, so, and because there's a large suite of such data, we can look at, slightly different phase space just to make sure that we're not handpicking a particular weird phase space or data set. But basically you got consistent results. Basically, if we want to quote a number, I would say the uncertainty is probably at 50 to 80% for Genie, and people, let's say 20 to 30%. And this is not good because remember the experiment should operate at about 5% precision. And this is only one part of the input. So we should definitely improve. And just to make connection with the first part of my talk. So remember that the actual cross-section calculation we need is the fully exclusive cross-section. Because we need to know what happens to the protons, pions, and neutrons, and that informs neutrino energy reconstruction. What we don't need is the inclusive cross-section, meaning that to know what happens to the lepton. But what I just showed you are inclusive measurements, because that's the only data set we have. So even if you don't compute these things, hopefully it's intuitive to see that it's easier or should have smaller error bar to compute inclusive cross-section. The more exclusive you go in phase space, the harder it is to get things right. So for what's actually needed for neutrino experiments, we would expect the uncertainties or mismodeling to be even larger than what we just saw. But we don't actually know how to quantify it because there's no existing data we can use. So that's still an open question. Any questions about that?
Yeah, just to clarify, so if you go back to the plots that you had, so I'm a bit confused why the deep inelastic scattering contribution is larger at smaller Qs in that plot.
You meant the one on the right.
Yeah,
Great question. Yes, it should do this. So what this is, okay, so I simplified this a bit. It actually has two components of both combined called DIS. One is the normal DIS. The other is the so-called one pion production, non-resonance one pion production. Meaning that, so this is a delta peak where you just produce a delta, but you could also, there's additional tree level interaction where you produce a pion directly. And that part is not well modeled. So for this particular example, this is what that component is. How they get that is actually, they just look at, single pion production data, like a scattering data from JLab. And then they have their own resonance model and they do the subtraction. Total minus resonance or whatever gives you is what they call the tree level interaction, which is why it has, the peaky structures.
okay.
So what they call DS is the sum of both.
Oh, okay, makes sense. Yeah,
Yeah.
thank you.
Whereas the one on the left is how they actually model DS.
Yeah.
Any other questions? Nope. Okay. So the conclusion is the uncertainties are pretty large. If we have to put a number, it's something like 50% and possibly even worse. And there's no theory calculations that give you uncertainty, so we have to rely on comparing to exclusive data, which we currently don't have. So hopefully we will have more exclusive electron scattering data, so that gives us a handle on the size of uncertainty. Okay, so but given that there's clearly quite large theory uncertainty, how do they actually impact physics searches? And here I will use a new physics search as an example. So first, what I showed is not totally fair in terms of how large the theory uncertainty is, because, well, obviously in experimental analysis, we know there's large uncertainties and there's ways to mitigate them. So this flowchart basically shows how they're mitigated. So what experiments actually do in all current long baseline experiments is the following. So let's start with a theory calculation, say default genie as example. Then we can we have, combine that with flux, detector response simulation, etc. This default theory can predict a spectrum in near detector. And obviously assuming that standard model physics, nothing else will happen. But also in near detector, we have large amount of data, very high statistics. So we can compare what we observe in near detector to our prediction. And if there's discrepancy, we can fix the theory by, tuning the model parameters. And this is called near detector 2. And then after tune, in near detector data would tuned theory would agree with data. Let's call this Gini prime. And then they will use this Gini prime to predict what happens in the far detector and do the oscillation experiments, do the oscillation analysis. So what I just showed, the theory out of box is not what experiments have to use. I mean, this is the whole point of the near detector, right? Because we know the uncertainty is large, so we try to use them to fix some part of the theory. Okay, so what this means though, is that if we're trying to do a phenomenological study of making any sort of connection between the cross-section calculations to experimental analysis, we need to take into account tuning. This is a significant procedure in the whole analysis. But this makes it difficult for a couple of reasons. First, there's no agreed upon way to tune. Once you see a discrepancy, each experiment has its own way to tune. And sometimes for one experiment, even for different analysis, the tuning are a little bit different. So there's no one procedure one can study. Also, tuning is simply just not public. So there's a practical difficulty. And in fact, just in the summer of 2020, NOVA became the first experiment that actually published their tuning procedure, which is really great to see, because it's not if the tuning has to be used by other collaborators, by other people study this, it has to be released not just with words but also with like code. So which is a major undertaking. So NOVA published the first tuning procedure in 2020, which is why in our study we use NOVA as the example. So their main tune is the following step, just to explain this. So again, when we take default Gini with, normal part of detector simulations, we can predict some sort of event spectrum. And what's basically here, the data is again the little black points, and the total theory is the top of the yellow thing. What Nova assumes is that, so this is different interaction channels that's in different colored regions. What Nova assumes is that all the interaction channels are known and correct. Let's say DIS, resonance, they're all perfectly modeled. The only discrepancy that's causing this is the mismodeling of MAC, meson exchange currents, which means the neutrino is interacting with a nucleon pair. Instead of hitting a single nucleon, it's basically hitting the proton-neutron pair, converting that. Then they project out onto phase space of 3 momentum and energy transfer, and bin this into like basically 200 bins, and in each bin multiply some random weight, so that in the end the event spectrum match in this energy histogram, just by changing the weight of the MAC events. So a couple of things I want to point out. The first is this, you can already see that this is a pretty significant change to the cross section. The MAC interaction changed by like more than a factor of 2. You can sort of see it. Another problem, which is probably more significant, is that this weighting is really not well guided theoretically. It's not consistent with any specific model. And because it's binned by like 200 bins, you're essentially adding 200 unphysical degrees of freedom, which you can imagine can mess things up. But this is the procedure that they did. So we follow their procedure trying to study the following. So if there's new physics in the new detector, does this procedure wash away? Can you still recover the new physics? Or would you bias it? So we just took a couple like most standard example. The first one is stereo-neutrino oscillation. And just so that we have new physics signature in the new detector, which that's how motivated us to choose the specific stereo-neutrino parameters. And the signature you would see is the typical neutrino oscillation. That's the blue line. There will be oscillation probability, and with some missing neutrino flux at about 2 GeV. That's the Nova flux peak. So suppose this exists in your new detector. Can you recover it? And the procedure we'll follow is the following. So assuming you have a reasonable amount of modeling of the cross section with additional stereo-neutrino signal in your new detector. Now, when you do a physics search, you know that there's stereo-neutrino, there's also mismodeling. So then you try to tune away some of it, following their phase space tune, and then going back to the search, see if you can still see the wiggle. Okay, so just to show that a little more concretely. So in this case, the left figure shows if there's perfect modeling, no cross-section uncertainty, just a stereo-neutrino signal. Okay, so you start with your standard model background, that's the blue line of neutrino interaction. Then, because there's stereo-neutrino ER data, you can see the mock data would be a little bit below your standard model line. The difference is just stereo-neutrino oscillation. And now when you try to find stereo-neutrinos, you try to tune away some of that. And after tune, you basically get to the red line. It gets closer to the data. And then using your tuned Gini, you try to recover the stereo-neutrino signal. And that's shown on the bottom, because if you try to find stereo-neutrino, you will look for wiggle. And here, basically what you see is that the wiggle does get shifted a little bit, but the basic feature is still there. You don't tune away a wiggle completely. Okay, so that seems to be good news. But this is done under the assumption that there's no mismodeling of the cross section. So we are doing everything with the same model. Yes.
Sorry, where's the wiggle that we're looking for in this?
Yes.
Okay, that one, okay, cool.
Yeah, the big one. Yes. So with no tuning, just standard oscillation, you will just get this blue line.
Okay.
And then if you tune, you basically recover the same shape, just shifted, reduced in magnitude a little bit. Okay, so this is if you have no mismodeling. However, if there's some part of cross-section mismodeling, like in real case, in which case we mimic the effect by using 2 different event generators to generate data and to do the analysis. Then what we see is things get messed up a little bit. you can still sort of see the shape of the wiggle, like a bigger bump here and a smaller bump here, but obviously that twisted a little bit. And the reason is that the theory mismatch, simply due to cross-section modeling, creates some sort of wiggle on its own. And why would theory mismatch give you some feature? Well, as we saw before, because this region is not done by one single calculation. There's a bunch of different models, a bunch of different channels that got added up. So there could be intrinsic feature in the mismodeling that just looks sort of like a wiggle. Okay, so if we translate this into a sensitivity study, this is one optimistic case that you hopefully would want to see. If there's a real standard neutrino signal in nature, and that's the input parameter of the cross. And when there's, everything's perfect, there's no cross-section modeling, no tuning, then we would recover this black line. That's just a sensitivity due to statistic and normal systematic error. If there's some mismodeling, but you don't tune it away, you would still recover a standard neutrino signal, but it will be shifted. So that's the blue circle. And then if there's mismodeling, but you try to tune it, like what NOAA does, it seems like you actually counterbalance the effect of the mismodeling and basically recover the true region. So in the end, with the tuning, the red curve is pretty close to the black, which is pretty good. So they seem to see, tuning actually works. It doesn't tune away new signal, then actually counterbalance some of the cross-section problem, which is great. But this seems to be happen to be a lucky case in our example. So the right one, the only difference we just change parameter space for the stereo neutrino. Nothing else changes. The mass go from 5 EV squared to 2 EV squared. On the right, we see the following. So the real region of signal is this, again, black. If we don't tune, what you can recover, what you would get is that mismodeling alone would actually exclude existence of a stereo neutrino, instead prefer no new physics case. If you do add tuning, it helps a bit. What you would recover is this region, which is still not very good because first, it excludes the true parameter space, and second, it actually opens up to like really, really high. So basically what the story tells you is that tuning doesn't wash away the specific oscillation signature, which might be a little bit surprising because it seems like tuning adds a lot of degrees freedom. So that seems to be good. And when there's no cross-section mismodeling, tuning seems to be helping a little bit, which is great. However, as we know, there's definitely cross-section mismodeling. And in that case, tuning seems to be helping a bit, but it certainly doesn't solve all the problem. And you could miss the real parameter space of the new physics you're looking for. Okay, so that's one study. And because we're trying to look for different signatures of the new detector, we tried alternative signal. And this is the neutrino-Nucleus scalar case. And I'll skip the model part, just focus on the signature. So the idea is that there could be a new particle that's a scalar that could interact with neutrino. So for neutrino interaction, it could just radiate off. And we would be looking for events where it's just normal standard model neutrino interaction, and with a new particle carrying away a lot of energy and momentum. So the signature for this case is just events with large missing transverse momentum. So similar to the model searches in the collider case. Okay. So just to be a little more concrete, how would they normally look for such events? Such signal. So we can make all the standard model neutrino cases, and the signature we're looking for is missing PT. So of course, normal standard neutrino interactions gave you PT, so there's some standard model background that's blue. And the new physics tend to peak at slightly higher missing energy, and that's the red signal. So the first thing you have to realize for this search is that obviously, by definition, we're looking for new physics. That should be a small fraction compared to standard model case. So as this case indicates, standard model is 3 orders of magnitude higher than new physics signal. That's expected. Okay, so no problem. The first thing we need to do is we need to cut the standard model background. Okay, and depends on, the specific phase space of new physics, you can do standard, you can do signal over background, study and then find the phase space where there's higher signal events. So let's say on the right, you do the cut and you have to cut pretty aggressively on the background because you need to cut about 3 orders of magnitude. The problem is once you go to a little corner of the phase space for the standard model, we're back to the problem I said before. The more exclusive we go to phase space, the more stringent requirements on the theory calculation. So theory tends to do better if we integrate over the whole phase space. If we go to 1 in 1,000 part of phase space, there's no control on the theory, which is exactly what we see on the right. Once we do the cuts, because we cut event by so much, the event generator discrepancy becomes much larger than the new physics. So hopefully that, any questions about that one? Okay, so translate into a sensitivity region. Again, similarly, if we try to inject a very, very strong new physics, so a coupling of 0.5, very high, so very strong new physics. And if there's no cross-section mismodeling, and we just do the analysis and we will recover this gray band. Again, this is just reflection of statistics and systematic errors that we include. But if there's mismodeling, and whether we tune it or not, we would strongly prefer no new physics. And in the case of tuning, we actually would exclude the new physics by way more than 5 sigma. So again, just to emphasize the lesson, because this one is actually fairly generic to most new physics searches we can carry out in near detector. Again, because there's large standard model neutrino background, and by definition, most new physics we want to look for is 1% of the strength. So they're a little bit. To find them at all, you need to do very strong cuts. So normally tend to go to some sort of phase space, corner of the phase space where standard model background is very low, so you can take out the signal. Which means the mismodeling, or the cross-section uncertainty will be huge in these little corners. So earlier we see that integrate over all phase space, we're talking about 50% uncertainty. So if we go to 1 in 100 part of phase space, it's going to be at least 5 to 15. And we're always looking for a weak new physics signal. So it's a very open question in terms of how will we go about this. And so hopefully someone will find the answer. Okay, so that concludes my talk. So hopefully I've convinced you that understanding neutrino-nuclear cross-section, and not just to give the theoretical calculations, but understand its uncertainty, also how the uncertainty impacts experimental analysis, is crucial for the success of this program. And the problem is that because the beam energy sits at around a couple GeV, there is no complete theoretical framework for this calculation, and we won't have it in the next 10 years. Meaning that not just the theory predictions are difficult, but also there's no well-established way to assess theoretical uncertainties. And trying to understand the impact is very complicated because there's complicated interaction between theory prediction and experimental procedure, including tuning. But we see a lot of progress in the field. For instance, the first one is that NOVA actually published their tuning procedure. And now with microBone experiment, they're also published their tuning. And because each experiment used different tuning procedure, the study has to be done one by one, but it's on the way. So thank you.
Okay, thank you, talk. That was really interesting. Does anyone have any questions?
So when you were talking about the MEC, the MEC tuning that the generators are using, what would it take to actually measure the cross section for those events rather than use the tune like meson exchange current events?
Well, that's a good question. It's very difficult. So the idea is it's not just applied to Mac specifically, but it's basically for all the channels. Again, the story is down to first we need to have some sort of theory to calculate this interaction with. And let's say even for the best case that we have quasi-elastic, because it literally it's this matrix elements. we have to get the vector currents from electron scattering data, which presumably we have. But additional problem is even if we have these, we still need the axial form vectors. And that there's, in principle, two ways to get. One from theory. The only theory that can compute this is lattice QCD. And I'm not lattice QCD expert, but if I just take what my friends say, then maybe they'll get some of the low energy ones in the next few years. But there are many, many high baryon states. And I think it's gonna be extremely challenging for them to get to, like, say, most of them in the next 10 years. So that seems very, very difficult. Oh, another way, if you can compute it from lattice QCD, you can just measure it. But the most direct measurement would be neutrino-nuclei scattering. Well, which we had some bubble chamber data back in the 60s and 70s, but there's two sets of measurements, one from Argonne, one from Brookhaven, and there's some discrepancy between those data sets. Back in the day, the data set also had very large error bar. So I think people try to extract as much information from those data sets as we've already had. Well, now we don't have hydrogen tank, so it's not clear how can we get new neutrino scattering data. So what we can do is use nucleus target, like these experiments, NOVA T2K. Of course, there's a lot of neutrino scattering, we can get them. Which, you can see it's just quite complicated because, these experiments themselves, like just to make these measurements, they suffer from cross-sectional uncertainty on its own. And also, these experiments are not, like, it's hard to measure neon angle to better than a couple of degrees in the neutrino experiment. So they just always have pretty large error bars on both x and y axis. And we're trying to fit many such form factors. So it's not clear how far that can be pushed. So
we'll always have to tune. Is that
Sorry?
what it is? We'll always have to tune.
yes. Yes.
Along those lines, so you mentioned that each experiment has their own tuning procedure.
Yes.
Does that mean? So the point there is you cannot use the same tuning for different experiments. It has to be done separately for each experiment.
Not quite. So right now it's okay. So I would say ideal case is that even though the theory is difficult, we would have some sort of, let's say, magically somewhat of a reasonable theory framework where you would have real physical uncertainties, like let's say the uncertainty of form factor. That's a physically motivated thing. And if we have that, then hopefully different experiments would actually use the same tuning procedure because the real physical uncertainties are those by theory. So you would just, each experiment would tune F1 and F2 and etc. So that's well motivated. The problem now is just that's not the case right now because we don't have that kind of theory, or we're not even doing like the best we could actually. So then experiments have no theory guidance. So then they just come up with like ad hoc tuning. So right now, if we were to do simply, I meant if we were trying to do phenomenological study, like we try to say, new physics, like NOVA tuning impact on new physics, we have to contact each experiment to get their own tuning procedure. But one of the goals of this long line of work is hopefully find a better way to tune and push experiments to use that more physics motivated.
So in principle, the tuning procedure, if it is defined prior to running the experiment and running the analysis, they should be the same.
Correct.
Across the experiments.
Correct. If we had a very good theory model, at least for part of the parameter space we actually do, they should come with a well-defined set of parameters that they should tune and stay in this set of parameters and not outside. Of course, once you tune within that range, somewhere it should agree with data. I think right now the problem is like there are like these models do come with some tuning parameters. It's just you can vary them, but they don't touch the data. So then experiment has to add additional tune.
Right.
Yeah.
So to extend that in your work, when you have looked at the at what these tuning parameters, how they affect let's say sterile neutrino search.
Uh-huh.
You've looked at the near detector data with NOAA.
Correct.
Could you do the opposite of what these experiments do, where you use the far detector data and compare that to the near detector data, because that should also be tuned, right?
Yes, very good. So that's what we invested, especially for the sterile neutrino case, because
Oh,
what
I
we
see.
found is, because it's a wiggle. So near detector has some wiggle, but presumably if whatever change you do in the near detector, it will also have a non-trivial manifestation in the far detector. So that should give you additional handle. The problem we run into, however, is flux. Again, similar problem because again, new physics by definition is so tiny.
Yeah.
There's almost nothing that can reach far detector.
Yeah.
Which is really the problem because, if we had additional detector, that obviously will give us a lot of handle, but that's why I mean, there's so many new physics where, phenomenon studies, people propose to do them in near detector because of the huge flux.
Mhm.
But that also means you're on your own, there's only one detector there. Far detector doesn't help much in terms of leverage.
But maybe SBN program, given that the detectors are not that far,
Yes,
you can find that useful. perhaps.
yes, I think SBN whole program would be very interesting because of the comparable issue baseline. Yes, exactly.
Very cool, thanks.
Any more questions in the room? So I'll check Steve. Yeah, look like the same questions on Zoom. So maybe we can thank Shirley again.